Now, I want to spend a few minutes comparing and contrasting the disk method versus the shell method. Because like I said, there are times when the disk method could be more advantageous and sometimes when the shell method would be more advantageous. So let's just take a look at what they're doing. So let's start off with obviously the disk method here. Now, the first thing you want to note is that the disk representative, or in the disk method, the representative rectangle, or that slice, is always perpendicular to the axis of revolution. So let's draw a couple of pictures and see what that means. If I have a function that looks like this, from A to B, and let's say this is C to D, and this is the piece basically that I'm revolving either around the x-axis or the y-axis. So first let's revolve this thing around the x-axis. If I revolve it around the x-axis, then the representative rectangle, which is actually thought of more of a slice right here, is in fact perpendicular to the x-axis. See, it's perpendicular to the x-axis. Now, if I took this thing, the exact same function, see, A to B, C to D, and this time I'll revolve it around the y-axis, then my representative slice, which give me that disk I'm looking at, is again perpendicular to the y-axis. So the disk method would result in this situation with a volume that's going to be equal to pi times the integral. It's perpendicular to the axis of revolution. I'm going to be going from A to B. I'm moving this disk along the x-axis from A to B of this outer radius, which we thought of as capital R of x squared, minus the inner radius, little r of x squared, dx. See, this is a function of x. Here, I'll be going from C to D, so the volume is going to be pi times the integral from C to D of this outer function is going to be a function of r. This outer radius will be a function of y squared minus little r of y squared dy. Now compare both these scenarios to the shell method. We'll try to draw the exact same thing. From A to B, C to D. This is the x-axis, this is the y-axis. Now, if I revolve this around the x-axis, see, if I'm spinning it around the x-axis, then the rectangle that I'm spinning would be parallel to the axis of revolution. Whereas here, try to draw the same thing again. A to B, C to D, so y-axis, x-axis. I have the same piece, but this time I'm revolving it about the y-axis. See, when I spin around the y-axis, then where is my rectangle that I'm spinning about it? Well, I'm going to cut this up into rectangles that look like this, and that is what's going to be spinning around the y-axis. So again, this is parallel to the y-axis. See, this is parallel to the x-axis. So this gives me a volume equals 2 pi times the integral. Well, if I'm going around the x-axis, the height is now a function of y. So this would be P of, or h of y. And then this midpoint is also in reference to y. P of y dy. Whereas in this case, going around the y-axis, see this, well, again, I write volume equals 2 pi. Oh, I'm sorry, and this was going to be from C to D. So this is going to be integral now from A to B. And you notice that in this case, this midpoint, what I'm thinking of as P, is going to be in reference to x. So it's going to be P of x. and the height of this will be a function of x. And again, if I revolve around the y-axis, this rectangle is parallel to the axes that I'm revolving. So you see, these will get you to the same place, but the thought process is definitely different. Here I'm slicing it, looking down here at a disc. Here I'm taking a rectangle and I'm going to spin it around, and here around the appropriate axes.